Today we'll be introducing a new series entitled Physical Optics, and we'll discuss the nature of light. This is part 1 of the introduction. Let us start with a well-liked, popular and widely known verse which says, "Let there be light," and there was light. Light was then divided from darkness. It is a quote from Bible, but let us mention that scientists wanted to investigate and wanted to get to the bottom of everything. And here the topic of discussion is light, to be precise, physical optics. Physical optics explains some phenomena involving light, assuming that light has a wave-like structure. Let us first address the question, what is light, in this lecture. Now, regarding this, in 1675, Newton's corpuscular theory of light was there, according to which a light source emits particles called light. Particles were also called corpuscles, and therefore it is called Newton's corpuscular theory of light. Now, this theory explained rectilinear propagation of light, according to which light moves from point A to point B following a straight line. It explains the phenomena of reflection, and it also explains the phenomena of refraction, which is a phenomena involving two media. This theory predicted that the corpuscles are pulled by the medium, and therefore speed of light is greater in a denser medium. This fact is not correct, as we know now, and therefore the question mark sign. Newton's corpuscular theory of light could not explain interference and diffraction. Just to remind, interference is production of a pattern, fringe pattern as we call it, which consists of a dark, bright bands instead of a uniform illumination, and is produced due to superposition of two light beams, while diffraction represents bending of light from straight path, which occurs when light in its path encounters an aperture or an obstacle. Now, it is not that any theory would explain everything. So this failure to explain interference, diffraction, was not a matter of great concern. Any theory, to be successful, has to get its predictions right, properly verified, that is experimentally tested. This is very important for a theory to stand the test of time. Newton was a celebrated, brilliant scientist who made a monumental and unparalleled contribution to science, in particular physics. He was like a sun in the sky, and his theories also stole the spotlight. Like his other theories, this corpuscular theory, in spite of certain odd predictions and anomalies, which we are not going to discuss, was forced upon contemporary theories like Huygens theory, etc. which thus did not get due attention. In other words, Huygens wave theory was overshadowed more by the brilliance of Newton as a scientist than by his rather fragile corpuscular theory. And this dominance lasted for a long period of time, as long as 175 years. So, for a long period of 175 years, light was thought to be obeying Newton's corpuscular theory. Now, in science, we had many instances when truth was suppressed either by force or by someone's ego. But the beauty of truth or beauty of science ultimately had the last laugh. Corpuscular theory, indeed, was a scientific theory, but it could not win the test of an experiment performed by Foucault in the year 1850, and therefore was rejected. In 1850, that is after 175 years of Newton's corpuscular theory, conclusively showed that light speed is less in a dense medium. And this was why Newton's corpuscular theory had ultimately to be rejected. So after rejection of Newton's corpuscular theory of light, Huygens wave theory of light came into prominence. It was given in the year 1678. So after a long period of 175, nearly 173 years, it was accepted. And it says that light source emits waves called light. So essentially light is a wave. Some other things also were predicted by Huygens along with the statement that light is a wave, and they are: like sound wave, light is a mechanical wave, which we now know is wrong, and hence the question mark. Now, since it was predicted or it was thought to be a mechanical wave, this automatically means that light requires a medium for its movement, for its travel. And that medium was called ether, and it was named luminiferous ether. Luminiferous means light bearing or a light propagator. And some strange, weird properties were attached to this medium called luminiferous ether. The name was given by Hooks. The properties of ether were as follows. It was an all-pervading or omnipresent medium. It filled entire universe, so it was a space-filling medium. Atoms, molecules, and everything were within it. All planets, stars moved through ether, which offered no resistance to their motion. In other words, ether was perfectly transparent. And we know that if a substance rotates in water, then the layer of water in contact with the object also rotates. But in case of ether, it is not dragged by moving bodies. So ether, apart from being transparent, it is frictionless, massless, weightless, it has zero density, it is perfectly elastic, and most importantly, ether is undetectable either chemically or physically because it has no interaction with physical objects. Another extremely important property that was attached to ether was that it represented an absolute frame. It was immobile, stationary, so it was absolutely at rest. This point we will not discuss in this lecture. Now, like sound, it was thought that light is carried from sun to earth by ether. So ether was a carrier of light waves. Another important aspect that was ascribed to light, that was attached to light, was that light was a longitudinal wave, like sound wave. Again, as per our present understanding, it is a wrong statement and therefore the question mark sign. Now, Huygens wave theory explained properly rectilinear propagation of light, reflection, refraction, phenomena of interference and diffraction, but it could not explain polarization, photoelectric effect, Compton effect. In 1817, Fresnel gave a theory that light is a transverse wave. This wave part was given by Huygens. This prediction was of Huygens. Now Fresnel attached to it that light wave is transverse, and then it explained polarization. So the transverse nature of light was instrumental in the explanation of the phenomena of polarization. Sound is a longitudinal wave and cannot be polarized. Again, light can be polarized and therefore it should be a transverse wave. Maxwell in 1873 came up with a new theory which he called electromagnetic theory of light. Let us recall that in 1864 Maxwell gave 4 equations which are the pillars of electromagnetism, and in 1873 came up electromagnetic theory of light, according to which a coupled electric field and magnetic field travels through space as an electromagnetic wave, and that represents light. Vector E, the electric field, is called light vector. It is eye sensitive and is responsible for most of the optical properties. And in 1887, Heinrich Hertz experimentally verified the existence of electromagnetic waves as proposed by Maxwell. Now what stands is that, at this juncture, what stands is that as per Huygens light theory, light is a wave, and this is all right. The statements that light is a longitudinal wave is wrong, as corrected by Fresnel. Another aspect of light that was attributed to it was that light is a mechanical wave. Now, this statement was contrary to Maxwell's electromagnetic theory, because according to Maxwell, light is an electromagnetic wave, and this was corroborated by the experiments of Hertz. Now, what about the medium called ether that was predicted as a carrier of light wave? Michelson-Morley in 1887 tried to detect ether through their famous experiment, which is called Michelson-Morley experiment. And in their experiment, they failed to detect ether. So the concept of ether was rejected outright. So light is an electromagnetic transverse wave. It propagates as electric and magnetic field oscillations and requires no medium for its propagation, since light is not a mechanical wave. Light can travel through vacuum as well as a medium. So the gist of what we got is light is a transverse electromagnetic wave. This wave part was predicted by Huygens, electromagnetic nature was predicted by Maxwell, and transverse nature was predicted by Fresnel. And this has been represented in this diagram. As mentioned, electric field is oscillatory, which means the E vectors vary in this pattern, and in a perpendicular direction the B field varies. So these are the B oscillations and these are the E oscillations. And electric field, magnetic induction, and the direction of propagation, that is vector E, vector B and vector K, they form a right-handed triad. They satisfy this sort of relation where omega represents angular frequency and vector k is the propagation vector, k cap being the direction of travel and k is the magnitude of the propagation vector. Now this theory of Huygens, Maxwell and Fresnel could explain the following phenomena exhibited by light, namely rectilinear propagation of light, reflection, refraction, interference, diffraction, as well as polarization, but strangely could not explain photoelectric effect, which was discovered by Heinrich Hertz in 1887. And photoelectric effect is actually the phenomena of emission of electrons called photoelectrons when a metal, also called photoathode, is bombarded with light. So if light shines upon a metal, electrons are emitted, and that is called photoelectric effect. This theory could not also explain Compton effect, which is essentially an elastic scattering of X-ray and a free electron. An X-ray of wavelength lambda, if falls upon an electron, then the scattered X-ray is found to have a greater wavelength, and this is the recoil electron. We will not go into details of these in this lecture. So this theory explained many things but failed to explain certain important experimental observations, namely photoelectric effect and Compton effect. In 1905, Einstein gave his quantum theory of light or photon theory of light. He used Planck's quantum hypothesis to explain blackbody radiation. Planck assumed that the oscillators which make up the blackbody can assume only discrete energy levels given by nh nu, where n is 0 to infinity. And from this description, Einstein got his photon theory of light. According to Einstein, light is a stream of particles called photons having energy E equal to h nu. Each photon has energy equal to h nu, where h is the Planck's constant of this value and nu represents the linear frequency of the light wave. Now here the photons, that is the particles, are not the corpuscles which Newton's predicted. So they are not Newtonian corpuscles, but they are photons that were predicted by Einstein having energy h nu. So it's a quanta, it's a bundle or packet of energy and also called quantum of energy. Now this Einstein's photon theory of light could explain properly the photoelectric effect as well as the Compton effect, but strangely it could not explain interference, diffraction and polarization effects exhibited by light. Let us now summarize the results. According to Huygens, Fresnel and Maxwell's theory, light is transverse electromagnetic wave, while According to Einstein's theory, photon theory of light, light is a stream of photons, h nu. So light has a dual character, and this is called wave particle duality. We cannot discard any theory. A strong evidence or experimental proof is there for both of these theories. For instance, interference, diffraction, polarization are important phenomena which are explained by this theory, assuming light is a wave, while photoelectric effect, Compton scattering are also another set of important phenomena which are explained well by the particle theory of light. Let us mention a few characteristics. Wave aspect of light and particle aspect of light are not contradictory but complementary. Now, wave and particle property are contradictory because while a wave needs an infinite amount of extension, a particle is localized in space. A wave extends from minus infinity to plus infinity, but a particle is confined to a particular point and therefore it is called localized. So the very aspect of wave and particle are contradictory. What we are referring to here is that the property that light has an wave aspect as well as the property that light has a particle aspect. This is not contradictory but complementary. We'll explain it further. Another property, the same property, can be recast when we say that these properties are mutually exclusive. Wave aspect and particle aspect cannot be brought face to face in the same experimental situation. In a coin tossing experiment, only one of head or tail appears, never both. So head and tail, just like the wave nature and particle nature, are mutually exclusive. Again, head and tail are components of a coin. A coin will cease to exist without a head or without a tail, though the coin shows up only one face at a time. In other words, head and tail, just like wave property and particle property, has a complementary existence. They do not oppose, but together they make up the coin, and in this case, the light. So this is the dual character exhibited by light, which is referred to as wave particle duality. Let us now shine light on to, say, two persons. One is Tom, the other one is Jerry, and ask them again what is light. Now Tom makes the light to fall on a double slit and sees an interference pattern. Tom will conclude that light is a wave, while on the other hand Jerry makes the light to fall on a photocathode and sees electron emission. So Jerry concludes that light is a particle stream. So do they contradict? Actually, the question does not arise if our past arguments are to be followed minutely. Now, what will be our conclusion? Our conclusion will be that what the nature of light is depends on experiment. We are doing the circumstances in which we are viewing light and the apparatus we are using. It is time to make a gist. In this lecture, we discussed Newton's corpuscular theory, Huygens wave theory, Maxwell's electromagnetic theory, Einstein's photon theory, and finally, the dual nature of light. In lecture entitled Ph1b, we'll go to Introduction Part 2, while in Ph2a, we'll take up Huygens principle. Let me end with a quote of the famous English novelist Teddy Pratchett. Light thinks it travels faster than anything, but it is wrong. No matter how fast light travels, it finds the darkness has always got there first and waiting for it. Whatever be the case, let us note that light moves at constant speed and there is nobody to overtake it. Thank you.